Okay, I think that's most people joined, so we'll get going. My name's James Richings. I've helped to organise this series of webinars on looking at some of the science behind the Archer Image competition. Today we have, I'm sure, to be a very interesting talk on the effects of wake steering or wind turbine flows. Presenting us is Dr. Sebastian Lemaire at EPCC and Dr. Andrew Moll from Imperial College London. I won't take up any more time, so I'll let them begin.
Hi. Okay, thanks. Yeah, so as mentioned, today I'm going to be talking a bit about the work we've been doing looking at wake steering for wind turbines and wind farms, as kind of some of the work behind the image you can see on the screen here. So I'll talk a bit about the background of that and the work we've been doing looking at optimizing and controlling these wake steering strategies for wind farms. And then I'll kind of pass over to Sebastian, who's going to talk about this very nice visualization that he kind of made from some of the data sets we've been working on with this kind of wind farm wake steering and kind of how he did that. So first of all, the reason that we're looking at this problem is the wind power is kind of been growing in importance in the UK for generating electricity. And so more and more of the UK's electricity is being generated by wind power. You can see here over the last 20 years how it's grown as a proportion of kind of the total energy generation, and it's forecast to continue growing in order to kind of meet net zero targets. We need to kind of transition away from burning fossil fuels and generating more of our power with renewable sources. And in the UK, there's quite a big focus on doing that with wind power. There are kind of a number of wind farms already kind of located around the country, and you can see on this kind of nice visualization here on the right, kind of where they're located, and there are restrictions in place on where we can kind of build more of these wind farms. So ideally they have to be situated locations kind of close to land or close enough that we can run the power cables, and also at the moment in areas where we have quite shallow sea, and then there's other restrictions about where they're placed as well. So there are only certain areas around the kind of coastline where we can implement these offshore wind farms. And so one thing we want to do is try and maximize the amount of power we can get from the wind farms that are already installed and future installations of wind farms, to try and increase the amount of power we're getting from these wind farms. One of the problems that we have with wind farms is the kind of wake effect. And this picture here is a kind of nice weather condition that has kind of revealed this effect quite nicely. So this photo was taken of the Hornrevs wind farm off the coast of Denmark, and in it you can see the kind of cloud inversion is interacting with the wakes from the turbines, and so you're able to see them. And if you look, you can see behind the kind of these turbines at the front, the flow is being disrupted, and so you get this region behind the wind turbine of affected wind, where the wind is kind of slower and more turbulent. And so each of these wind turbines has a wake associated with it, where the wind has been reduced. So in these areas, we then have a reduced amount of wind. And when more wind turbines are located, as they are in a wind farm behind these wind turbines, they're then experiencing non-ideal conditions. And this effect then kind of accumulates as you go further back in the wind farm. And so by the time you get to the back of the wind farm, the wind turbines are generating less power than, or quite a lot less power than they would otherwise. And this is kind of estimated to cost somewhere between 10 and 30% the power that could be extracted from a wind farm is being lost to this kind of wake effect. And so we want to mitigate against that in some way. So one way that's been kind of proposed to mitigate this is this wake steering, where we control the wakes in a wind farm by yawing the turbines. So if we take two wind turbines as an example, in this case, one directly in the wake of the one upstream, in this wake we have a velocity deficit. If we kind of tilt or point the wind turbine not directly at the wind but at an angle, we can then deflect the wake to the side to some degree, and therefore kind of reduce the effects of the wake on the power output of this kind of small wind farm that we have here. And so this is something that we want to kind of investigate further. And so in this work, we kind of turn to simulation and to try and kind of simulate this and look at the effect of different yaw configurations in a wind farm. So for doing this, we use the turbulent flow solver XCompact 3D, which is a 4-Tran based flow solver for studying turbulent flows. And it can do direct and large eddy simulations. In this work, we focus on the large eddy simulation implementations of this. And it's scalable up to hundreds of thousands of CPU cores due to its use of the kind of 2D pencil decomposition. And this enables us then to look at the kind of turbulent flow features that we see in the wind farm. So XCompact 3D also has a number of different models within it that can be used to model the effects of wind turbines. And so, namely, these are the kind of actuator line model and the actuator disk model. And these models kind of model the wind turbine in different ways. In the actuator line model, we replace the geometry of the winds of the turbine blades with lines that, or representations of lines in the solver that then kind of impart the force on the flow that the blade geometry would impart. And so this then has kind of for a three blade wind turbine, 3 lines that move through the domain, imparting these forces on the flow. The actuator disk model is a simpler model that doesn't kind of move the blades individually, but instead models the effects of the wind turbine as a porous disk located kind of over the swept area of the turbine blades, and imparts the kind of the force of the blades as a kind of time averaged effect over this disk. And so this is a less accurate representation of what's going on, but still captures these kind of far wake effects, but it kind of loses some of these closer wake effects that you can capture with the actuator line model. And so in XCompact 3D, we can use these models for the wind turbines in a wind farm and simulate the turbulent atmospheric boundary layer with inflow condition from a precursor simulation. And so when we're modeling these wind farms, we have this range of complexities that we can capture. So I mentioned just now the actuator disk model, large eddy simulations, and the actuator line model, large eddy simulations that we can implement with XCompact 3D. And these are kind of fields you might expect of the wind speed from those. We can also use analytical wake models, which give us a mean field representation of the flow behind turbines as we kind of change the parameters. And so as we go through these, the more modeling assumptions that we make, the less accurate it potentially may be. But as we increase the fidelity, we also are increasing the computational power required for these simulations. And so when we take these different options, some of the work we've been doing has been looking at trying to optimize this yaw steering approach for wind farms. And so in this work, we've been combining the kind of analytical wake models with large eddy simulations of the flow around a wind farm, and combining these into a multi-fidelity optimization process, which then allows us to find kind of yaw configurations for the wind farm that give us an increased amount of power without having to kind of add more turbines. And so when we do this kind of optimization process, we kind of iterate through different simulations, choosing fidelities in this case, and the output of that is then a yaw configuration for the wind farm, where the front wind turbine is yawed the most, and as you go further back in the wind farm, it kind of gradually reduces, kind of in this manner in the center, the yaw angle of the wind turbines. And when we do this, we can see that the power output of the first wind turbine is dropped, is reduced, but all of the subsequent wind turbines have an increase in the amount of power that they're generating. And this then compensates for that initial drop in the power output of the first turbine. One thing that we can see in this plot as well is how when we use the large eddy simulation, we're capturing physics further downstream in the wind farm that we're unable to capture with these wake models. And so we're then exploiting different physical effects than we can capture with these lower fidelity models. So we really need, in this case, the large eddy simulation gives us a greater power improvement than just doing optimization with the simplified models. So we kind of require the LES in this case to get that additional gain. Another thing we can do with this is, rather than look at optimizing for a static case, we can actively control the wind turbines to dynamically adjust to varying inlet conditions and control the wake steering in a dynamic fashion. And so we do this using a reinforcement learning approach to train a controller that kind of senses the flow around the wind turbines and then reacts to that to increase the power that the wind farm can produce. And so this is an example of just a 3 turbine wind farm, and in this case we see power improvement of the wind farm that's twice as much as just doing a static optimization. So we're about to increase even further the amount of power that we're generating in these wind farms. So with these kind of optimized wake steering strategies that we've been finding with the Bayesian optimization, and then more recently with the reinforcement learning controllers, what we wanted to do is kind of have a nice visualization of how this effect is working. And so we did an actuator line model simulation with XCompact 2D of a 2 turbine wind farm in a neutral atmospheric boundary layer. And then kind of Sebastian created this nice visualization, and he's going to talk a bit more now about kind of how he created that visualization. But we can see when we look at the power output from the simulation of the 2 turbines, when the turbines are kind of aligned with the wind's direction, we get a total power output of this red line. And you can see the first turbine has a much higher power output, and the second one a lower power output. And when we run the optimization and then use those optimized yaw configuration for that wind farm, the power improvement of the total wind farm is improved above that baseline, and it does that by kind of increasing the power output of the second wind turbine, even though the power output of the first wind turbine is reduced. So that's kind of an overview of the work we've been looking at wake steering for wind turbine flows. And I'm now going to kind of pass over to Sebastian to kind of explain how he created this visualization.
Great. Yeah, thanks, Andrew. Let me share my screen. Cool. Yeah, hopefully everyone can see that. Don't be alarmed by the number of slides. Some of them will be really quick to go through, so it won't take an hour to go through 60 slides normally. So yeah, I'm going to talk about the visualization itself, how it was made, and basically going from taking data from Andrew and then making this kind of visualization. So first, let's look. Yeah, if you haven't seen it already, this is the video that was produced. So yeah, you have 2 sets of wind turbine in a row, so 4 in total, both in different conditions. So on the left, you have the one that are aligned with each other. On the right, you have the one that are steered, and yeah, and it also loops seamlessly, and it's so yeah, not much more to talk about that. We'll go into detail into how this was made. So yeah, how was it made? First, we'll talk about why was it made, because that has a large influence on of how the reasoning, like why it was made that way. And it's always good to ask yourself questions about why making something, especially for visualization, before making them. Then we'll talk a bit about the tools that were used. And at the end, I mean, most of the talk will be mostly about different steps involved and how the iterative process works for these kind of things. You don't, you don't just put everything in the tool and then you end up with the final render. It's a iterative process, and yeah, so we'll talk about all of that. So first, yeah, before any visualization is done, it's good to ask like a couple of questions to see a bit in which direction we're going. First, the audience. So the audience can be like other scientists, can be peers, can be also like kids, can be for outreach purposes, can be like the larger public. So it can be quite broad, or can be quite, and like knowing who the audience is can help like decide for a lot of things for the visualization. It can define what it will look like. It will, can define like how much explanation it needs to have, and all of that. In this particular case, the visualization was done for like the wider scientific community, for HPC audience in general, but it was done in a way that, like, I mean, you see, like it's a sort of realistic render, so doesn't require any prior knowledge on anything. The purpose of why it was made, it's also, I mean, that's it's fairly obvious, but it also dictates quite a lot of like, the audience, but also how it will be made. So in this case, it was submission, like before being a submission for the Ashatu competition, it was submission for the Art in HPC category at SC24. So SC is a it's a conference of supercomputers, and it was in the Art and HPC category, meaning that it was not meant to be didactic. It was not meant to be explanatory much. It was meant to be artistic in a way. So that dictates quite a bit. What looks at the end. If it was for a different purpose, if it was for outreach purposes, suddenly it would have looked differently in a sense. And also that sort of ties in with the message itself. When you make a visualization, it has to have a purpose, a reason why you're making it, in a sense. In this case, it was mostly to show visualization capability, show that that kind of visualization was doable, but also mainly it was designed to look nice and look artistic in some way. And that's mostly because it was submitted for the Art and HPC category at SC. Again, as I said, like if it was designed for more like outreach purposes, it would be explained a bit more. You would probably understand a bit more what's in the visualization itself. In this case, without the talk that Andrew just gave just now, it's kind of impossible to understand what's happening. And that was not really, understanding what was happening was not really the purpose of it, because it was only designed to look nice and to show that what was doable on HPC simulation, in a sense. And finally, and last important question is the support. So how will it be communicated? If you're about to submit like a paper in a journal that will have a white, it will be an image on a white background. If it's a video, it will be different. If it's something to be displayed on large screen, it will be different. So in this case, it had to be a 30-second video. And it will be displayed on large screen at the SC conference. That was the main, the main pitch in a sense. And so knowing that, you can make changes on how the thing will end up looking like. Again, if it was like for a paper, it would have looked really differently. It would have looked, the same and the same thing. So all of these questions are good to ask at the beginning, to ask yourself at the beginning, so that it helps with like making decisions later on in a sense. So yeah, once we have all of that stuff answered, we go through the main step when working with 3D visualization. So first step is importing data. So yeah, I will, this is sort of summary, and I will go into detail into most of these steps just now. So yeah, first step, importing data, working with environment and lighting. So you see in this visualization, the raw simulation from Andrew, or part of it, but a large part of this visualization is also what everything else is around it, and that's what makes it look different in a sense. Then we talk about the camera placement. What does a viewpoint change in terms of what it will finally look and what kind of message it can bring. We'll talk a bit about the material itself. So by material here, I mean the sort of smoky effect of the flow can be defined and can be refined in lots of different ways. The transparency, the colors, a lot of ways, and that brings different messages to the final visualization. Then we talk about animation. So when you animate, when you have a video instead of just an image, it brings a lot more work in a sense. So you have to animate. Yeah, if you're moving the camera around, you have to define the path where the camera moves. But also one of the main differences is that if you have a video, you have maybe like 500 frames to render and to generate, and you can't do that manually anymore. You can't just do one by one. So you have to automatize everything and script everything. So that's one of the main difference when you go to an animation. Then we'll talk a bit about color grading, so how to improve the colors on something to make it look different. And then finally, the rendering, so how was it rendered, what kind of hardware, and how much time it took, and all of that. So let's start with the tools themselves. So people working in the CFD world, so 3D dynamic, often know about PowerView. PowerView, I believe that's what Andrew used for lots of the visualization you've seen just before. It's a tool that is designed for scientific data. It's designed to process scientific data. It can handle a wide range of input and output files, and most of the things you run in scientific application on FPC, most of the output data will be able to, PowerView will be able to open them. And so, yeah, for example, this visualization here, I did that yesterday. It took me literally 2 minutes to do that. It's designed for that kind of visualization, and it makes it really easy to make something with that. And and so the look you have is also something that scientists will be able to understand and see. Though, if you want to change things, it has quite limited rendering capabilities. There's some ray tracing in there, but it's a lot more limited than what other tools have. And it's also have limited animation features. You can render animation, you can move camera around, but the way to do that is quite limited. The good thing is it has a Python API, so you can script everything and you can automatize a lot of things. So that's the first tool. Second tool is Blender. So that's what actually in this case generated the final images. It's an open source tool. It's free. It's designed primarily for artists and for the 3D animation and VFX industries mostly. So this is the reason why it won't handle most files people use in the scientific world. It handles files that are often used in the VFX or 3D animation fields. But it's all the advantage of that, in a sense of being animation and VFX package that it does lots of it's a really large toolbox. It can do modeling, animation, rendering, editing, compositing. It can do more or less everything in one single package, and it brings extreme versatility, and you can change every single aspect of an image, and you have like lots of freedom in there, and we'll see a bit what that means a bit later on. And final thing is also has a really good Python API, so you can script a lot of things as well. And other ways to script it. So I also want to mention, if you followed the Oscar ceremony a couple of weeks ago now, you've seen that Flow, the movie Flow, has been awarded the best animation movie or something. I'm not sure the exact name for it. And Flow was rendered in Blender. So it's used. It can be used for scientific application, but it's mostly used for now movies, but also any animation and VFX in general. So let's have a look at the pipeline itself. So how the data went from XCompaxVD to Blender. So it starts with a CompaxVD where in a XDMF and binary file. So XDMF is a metadata file that, and binary is what the actual data is in. So what Andrew gave me was these two files, with these two sets of files, with pressure and velocity in the entire domain. And it was like one set of files per time step. And so because these two files cannot be handled by Blender directly, I opened them in PowerView. In PowerView, I generated the Q criterion, which is what you actually visualize in the domain. Q criterion, it's a quantity that is processed from velocity, and that shows the turbulence behavior. It shows the swirls and all of that in the flow. And that's actually what's visualized in Blender. And so from that, exported a VDB file. So VDB, I'm not sure it stands for anything. Volumetric database, maybe, I don't know. But basically, it's called like a volume file in a sense. So it's similar to the first file we have here. It draws a Cartesian mesh on the domain, and in every cell you will have these three quantities: the pressure, velocity, those three components of velocity, and the Q criterion. And so from that, this is a file that is like usually used in animations or VFX to like render clouds, render explosions, fire. All that is usually done, can be done usually through VDB files. And so that's what was exported from PowerView and imported into Blender. Then with the blend file, which is the Blender kind of file, as the name suggests, and this VDB files, you can render images and then export that to, in this case, PNGs, but it can be anything. So I'll see the pipeline, how the data works flow. So once all of that, to start with, I started to make sort of a proof of concept of basically trying to work this pipeline and see, to develop it and see what we can, what kind of example, what kind of visualization could be made from that. It took me like something like an afternoon to do that. I was just using a small laptop, so it's not a highest fidelity render at all, but it was just to see, what kind of, to experiment a bit and see, if there was something to build something bigger from. And so it was the first step, that, and now I'm going to go through most of the steps I showed you in the previous slides, and we'll see a bit. What it means for this visualization in particular. So the environment and lighting. In this case, the environment. So everything beside the simulations themselves is quite large. So there's the sky and all of this. There's the wind turbines, and there's the ocean as well. The ocean, the sea simulation here, was not done. Was not taken from the XCompaxVD simulation. It was something rendered in Blender itself, done in Blender itself. So the first thing, let's talk about the sky itself. What I use and most people use is what's called HDRI images. So HDRI stands for High Dynamic Range, meaning that it's a 3D image that you can put in the outside of your domain that has also sort of light information, and it can light your scene. So it also acts as lights. If you have the sun in your sky, it will you see the color of the sun, but also like act as a light for your scene as well. The good thing with 3D HDRI images, sorry, is that there is like large. People have done lots of those, and lots of them are available for free on websites like polyheaven.com. So you can browse there, and you have different kind of sky and other things. What you can do is you can rotate your sky. So, for example, if you want the sun to be somewhere else, you can rotate it and move that around. You can also completely change the sky. If you want to have a sunny day instead of a sunset, you can just go from this to you just load a new file, and it will completely change the atmosphere and the scene itself. And when you add the simulation back in, it completely changes the colors and everything, because all the lighting is dictated by this sky itself. So if you go back to the original image that was final image, and back to that one, just changing the sky completely changes the entire thing. The next thing is the ocean simulation. So this was what you see at the bottom. This was done in Blender. Again, Blender, it has like a chemical ocean simulator, which lets you tweak the height of the waves, how fast they go, how collinear they are. Lots of fun details. It's not scientific at all in terms of ocean simulation, so I would never use that for anything scientific. But it's designed to look nice and look realistic enough, and it's designed to be rendered really quickly in a sense. So you can generate entire simulation of an ocean really quickly. So it's a 2D simulation and rendered really quickly. And so it's not designed to be realistic. It's not designed to be physically realistic. It's designed to look similar H2 and ocean, and that's good enough for most VFX or animation applications. And in this case, also good enough in a sense. So changing the ocean, you see it will have, this is two different versions of different amount of details and everything in between. One of the other things is you can also add other lights. So you can add lights instead of light that are not existent in a sense. So in this case, if you see at the left on the second wind turbine, a light on the wall he has, like in the middle of the field, was added just so that it will brighten up a bit the image in this location to see a bit more. To see a bit more. So this is in this case, it's a light that's not realistic at all, but it's still useful to highlight things. So you can also add lights. And the final thing in this environment is all the wind turbines. As Andrew said, the simulation used line models for the wind turbine, for the blades. So the turbines were not physically there in the simulation, but we can make them visible in the visualization itself. So all of this environment and lighting helps bring a context to the scene, brings a sense of scale as well. The height of the waves and these kind of things will help understand how big things are. I think that's one thing that is actually not done really well in that particular visualization. Like, I feel like the scale of the ocean is not really well tuned for the wind turbine. Something I would have wished I had more time to tweak. Having something photorealistic also helps with immersion and help a wider audience understand what's happening, and also helps them engage with the visualization. If you compare that to a more scientific approach, more scientific visualization with a white background and all of that, it's a bit less approachable in a sense. So that helps with that, and also the lighting and the environment helps. You can like play with the colors there to have something a bit more visually pleasing. Here, most of the color are blue and red-ish, and it's the usual, orange and blue is like the opposites of the color wheel. So it's a visually pleasing set of colors in this case. So that's all of this comes from the environment and the lighting. Then next thing we'll talk about is the camera placement. So where how setting the camera change how the visualization looks. So that's that's an image that was rendered at the end. Camera. There's a couple of things that are important to think about, or at least have in mind. Is the location brings also a sense of scale. Depending where the camera will be, you will see more or less how big things are, and that's a good way to also have some reference in a sense. And so here it was put at sea level for realism in a sense, to make it look like it was taken from a ship or boat nearby or something like that. If you have the camera higher up in the sky, it could mimic something like a drone shot or something like that. Oh, that's a C not a K here, sorry. It couldn't, it would look different. I feel like in this particular case, you won't understand as much the height of the wind turbines. That's why I prefer to have start at the bottom before going up. You can also be completely on the other side and from the sides, something like that. Here it's quite good. You see quite well how far the turbines are. You can understand that. You understand a lot less how tall they are compared to, because you're further away, you're so high up. It's hard. It's hard to understand that. So you lose sense of height when you are further away in a sense. Though it can bring more, you see a bit better how the flow develops. So drawbacks. It's always compromises. You can also be really close and have a wide angle lens. So in Blender you can set every camera settings as if you were a normal, a real camera. So you can set the depth, not the depth of field, sorry, the focal length, sorry, of the camera, of the lens. So a wide angle lens will look like that. You'll be really close to it. And then that's what I had before. And then you can also have be further away and have a longer lens, and that will sort of compress the background, so you see a lot less a sense of direction. A sense of sizes. But it can be also more realistic for some applications and for some cases. So it's all of the things are things to think about. If you want to have something that looks realistic, it's good to have a camera in a location that would be realistic as well. So try to mimic where a real person with a camera would have been to take the shot, in a sense. In this case, it can be on the ground to take a photo from a ship, from a boat, something. The final video you saw earlier didn't really have that in mind. You could think it's done via a drone shot or something like that, but you have a bit of decoration there. I think that's also a reason why it's not. There's things to be improved on that video in a sense. So it's also camera placement can also help communicate scale. If you're too far away with a long lens, it will things won't show as well in a sense. And setting things similar to what you would have in the photographic context can help in a sense. We'll talk quickly about color grading. So color grading, it's it's a post-processing step. So once you have the render, the image rendered by Blender, you can color grade to change how the image looks. So it can be adding contrast, adding saturation, all these kind of things. It can also, in case of 3D renders, it can be composition and color grading are useful to try to replicate camera defects. So cameras are not perfect, but they are a bit more perfect in a 3D environment like Blender. So if you want to replicate some of the defects of real cameras, that can be there as well. And also, it's also to convey a mood, convey the right atmosphere for the right message, what you want to show. So this is, in this case here, the image just directly outside of Blender without color grading itself at all. And this is what the final image looked like. So it's very minor differences. You can see flipping back and forth to see the original one and the final one. One other thing I added here, for example, was some bloom on of the highlights. So usually highlights on cameras they have a sort of blooming effect where the light will spill a bit on other things, and in this case it helps marry a bit the simulation with the background. That was what was added here, and then you can also go further, like do more things. In this case, I think it's like a bit too much. Like the colors don't look as nice anymore; they look a bit too artificial. So yeah, but you can do even more changes. Yeah, let's now talk about the smoke. So by smoke material, I mean the smoky effects in the sense of the flow, what you see here. And we see like different steps, basically throughout the process of making that video. I rendered sort in the middle, as I rendered every time I had a new result, a new visualization, I export the file. And so I went back through all the files I exported and then to have a look at them. So this is sort of the first render I did. That was a proof of concept to see how it could look. And then little by little, I sort of try to improve things. The second one was this one. So in this one, I added different sky. There was now an ocean simulation, and the let's call it smoke. It's not really smoke, but the smoke here looks like that. One of the main issue I had with this is that the smokes look a lot like way too much like smokes, and that's not really the right message. You don't want to like imply that wind turbines brings a lot of pollution. Like this looks like a pollution cloud in a sense, and that's not really it's not really the right message for a wind turbine flow, and it's not really realistic at all as well. So even though, yeah, you will never be able to make something realistic because this is something that is not visible in real life. You can't really, unless you have some weird clouds like Andrew showed earlier, you can't really see that part of, you can't really see that flow. So it won't be realistic, but you want it to have a sense of yeah, making sense to be there. So yeah, another point of view up there, try to change the colors a bit of the things to make it look a bit like less like smoke. So bring some red into it, make it a bit too red. So I changed that to making more blue and a bit more transparency, so that it would be a bit less there, but it was a bit too transparent, so you could barely see the beginning here. So yeah, no, make it a bit less transparent, and then yeah, a bit. So changing a lot of things, see what looks good or not, and finally we ended up with that, which is like not ideal, not perfect, but I feel like it doesn't look like smoke as much as the other ones, which was the main point. And it's visually pleasing, like the blue and the orange from the sky are quite complementary and look harmonious together. So yeah, that's what went for that. And at the end, most of the image, when I exported this image, certainly I usually flip the image so that it goes from left to right. So it's usually a nicer way to direct the sight. In this part of the world, we read from left to right, so we're used to decrypting an image from left to right, and so having a flow of going from left to right is also helping understanding a bit more how it works. And so that was what the final material in Blender looks like. So in Blender, when I say material, it's what defines what the smoke effect is in a sense. So here it's all based on nodes. You won't have to understand everything, but basically at the end here, it takes a color and it takes a density. The color comes from the velocity of the flow. So here velocity is actually the velocity from the simulation itself. Each cell in your domain is a domain as a velocity, and you convert that velocity into a color. So lower velocity will be reddish, and larger velocity will be bluish here, and then you put that into the colors here. And for the density itself, so how thick the cloud is in a sense, this is done at this lower step here. So the Q criterion is the swirls and all of that, and then goes through a curve like this that will basically without that it will be sort of identity, so it will be a diagonal here, and if you have a large Q criterion, you will have a really large density, so it will be like a really lot thicker clouds. So what this curve means is that at some point after like here 0.3 or something, 0.2, the density won't be higher. So it means that's what I mostly tweak to to have a less smoky effect and a bit more transparency and a bit of a lighter cloud in a sense. Yeah, so that was mostly that for the for that. Yeah, I saw that. Yeah, I'm taking a lot of time for all of that. I will try to go a bit faster. Animation itself of the camera. So this is one of the first render of the video itself. And yeah, from here, see it really changes. So it was mostly to have a first idea of what were the main points I wanted to capture, and then it was already looping at the time, and then from there that's what the path of the camera looks like, the final one, not the one you just saw, and then yeah, after that throughout tweak and trying to smooth the motion and everything to make it look more pleasing mostly. I end up with that kind of animation. Yeah, we'll have to see all of it. We've seen quite a bit already. Yeah, the last step. Last step is to actually render the visualization itself. This was done on a 6 GPU system that is housed here at the PCC. It's using the script, some script that I wrote about a year ago in this folder here, that allows you to render in parallel, and with this kind of script, you can set, you're using 6 GPUs, and it will run 6 instances of Blender, each working on a different set of frames, and that way, you can render the entirety of the movie. In total, it was 590 frames and 590 frames in 4K. It was a requirement for the SC competition. Each of the frame took about 13 minutes to render, and it was each frame was rendered on a single 4090 GPU, which is a really beefy GPU. And so in total, it took the entire video, not really movie, but 14 hours to render on 6 GPUs. So it was all of the renders were just done overnight, and then it's the render next day. There are ways to throughout the day to have a faster iterative process. I was rendering a lot of really just smaller version, like 4K is a really large file. You don't really need that. It was only for the final outputs. But to have faster workflow, I would render a lot of smaller scale frames. And this is to make a comparison with the actual timescale of how much time it took me to do all of that. So initially, the initial proof of concept took about half a day. And then that's about the time it took for the rest. So environmental lighting, which included the ocean simulation, tweaking all of that, took about a couple of days. Script and automation, because you want to script everything, you want to be able to run everything automatically. It took me about a day to do all of that, and the motion of the camera and color tweaking about a couple of days as well. So this is most of the work. Once the first proof of concept is done, most of the work is just tweaking things little by little to make it better. So that's why it's a bit hard to take exact dates. But yeah, in total it took about a week and a half to do that. And for the machine it was rendered on here. Yes, final thoughts. There's still quite a bit of things to improve. I think, for example, adding new elements in the environment to bring a sense of scale can help. So in this case, adding things like a ship, for example, adding something like that, like physical in the domain, will help see how big the wind turbines are. That's something that I don't do at the time, but that can help often. So adding other elements so that it's a bit less empty can help. Adding a sense of, we're working the ocean again to make it have a better sense of scale as well, could help. Also, I feel like the color grading of the video is a bit too dark. And finally, the last thing is this video and images were used a lot as well outside of their original context. And even though, so the goal was for that competition, for that conference, because they were used a lot outside, in Insight, I would have probably made a bit different knowing that, because they are not self-explanatory at all. They're only designed to be nice to look at. But if they were if I knew they were going to be used outside, I would probably change things a bit so that you would understand a bit more what's happening in the video itself. Yeah, some resources. The slides will be available, so yeah, some resources to look at. And yeah, that's pretty much it. I guess now, if anyone has questions, that's the time to answer them.
Thank you very much, both of you. I think there's a number of questions in the chat.
Yeah, I can see that.
Do you want to read them out if you're going to answer them, or I can read them out for you?
Yeah. Okay, that's the first one. How big the XMF and binary files can be? Can you work on PVT's file as well in PowerView? Can you show two-pass flow turbulence as well? Two-phase flow turbulence. Yeah, so the size of the files themselves, beyond Drew, you can remind me. I think it was about like 1 terabyte per simulation, and there was 2 simulations. I think it's about that.
Yeah, I think something like that. I think it might be a few gigabytes per time step.
Yeah, something like that. So yeah, 3 gigabytes per time step, and there were 500 time steps. So it adds up quite quickly to something quite big. No, it's not. So it's not single file. It's you have 1 file per time step. So it's about a gigabyte. Let's say about a gigabyte per file, or a bit more. And then you have 500 of them in a sense. And yeah, you can work with PVTS file. Basically, anything you can use PowerView for, you will be able to use kind of with this kind of workflow. Everything PowerView can open, you can work with that afterwards. Yeah, two-phase. I mean, anything is like two-phase flow turbulence. Anything is like really doable. You will have a different pipeline. You will have different material and everything inside of Blender, but all of that is like definitely doable. I hope that answers your question. I mean, yeah, like you have 30,000. That's basically if PowerView can open that and output a single file or something, then that would work in a sense in that context. In terms of workflow, did you generate the blend file in an interactive session in Archer, or was that generated offline and then copied into the HPC? No, it was not. You didn't miss anything. It was not explained. Yeah, the blend file was generated interactively. It's almost impossible to do all of that only scripting. Like a lot of it is just the feel of like playing with the settings, playing with the button. You have to have a direct view of that. So all of this was done in an interactive session, not in Archer 2. Actually, it was done on the machine. Like the machine that was used for the rendering, it was a 6 GPU machine. That's also the one I use for the interactive sessions. You don't need a lot of computational power for that interactivity. What I use, for example, here, I didn't mention that, but I generated 2 sets of VDB files for Blender. So I generated one with a full resolution of like the final resolution, but also I generated a set of files that were a really low resolution of the data from Andrew. So and that very low resolution allows me to first like works on the like smaller machines, but also it allows me to like really to have faster to have everything loading faster and everything. So yeah, if you don't have access to a large system to do an interactive session, you can do that on a small machine, and then only once you go to HPC or to a larger machine, you use the real input file at all, like the full size of the file. That's what people use, and people use that a lot as well in VFX, and like use proxy to so smaller version of the input file so that they can work offline, and then once everything's set up, you can copy to HPC. That setup of working with both HPC and the local render is something that actually I'm working on these days to make it a bit smoother and helping with that. Luca, did you render streamlines possibly as surfaces or particle effect? Yeah, you could render streamlines as surface. I didn't do that. In this case, streamlines don't make a lot of sense when you have unsteady simulation. So because you have motion of the blades, streamlines don't have a real meaning in that context, basically because the flow is not steady, and so streamlines are designed when you basically integrate in space to like represent integration time, and so that was that don't make a lot of sense in the particular case, but that could be doable, and then it would be a surface. And you can, could manage that from ParaView. Particle effect would have been really nice. I didn't do that. It's something that would, like, it requires quite a bit more processing of the original data to have that. But yeah, you could definitely have basically have particles, and they would flow in the domain as if they were in the wind, and then you could see, you could visualize the wind with that. That's not something I've done, but it would be really interesting to see as well indeed. There any other question on my part or what Andrew also presented earlier?
I think that's everything that's in the chat. We're a little bit pressed for time, so I'm probably going to say we should bring things to a close here. And thank everyone for attending, and thank you both for presenting a very interesting talk. It's really great to see some of the outputs get visualized at such a high level as part of the HTTP service and other projects that are related to it and use the system. So thank you both.